This video explains the design of steel beam to support the following service storage load. The loads are applied at the shear center. Partial restraints are available at the support and concentric load points. Use the deflection limit span by 250. So loadings are given. W loading is 0.80 kilonewton per meter and 0 live load. P1, P2, P3 are respectively given in the kilonewton for dead load and for live load. The span of the beam is given 7000 millimeters. Location of point P1, P2 and P3 loads are given, and the section of this section for this beam is given here. Now to start with, first we're going to do the step number 1. We're going to calculate the load and structure analysis. Now the critical load combination is ED 1.2G plus 1.5Q, that is taken from AS 1170.0. On the strength criteria, page number 16, close 4.2.2, ED is 1.2G plus 1.5Q. That is written. Now first of all, we're going to work on the strength. So for P1, 1.2 times dead load 65, 1.5 48. So for P1, dead load is 65, live load is 48, so that is 65 48, it gives us 150 kilonewtons. Similarly for load P2 has a dead load 31, live load 96, dead load 31, live load 96 gives 181. Similarly P3 has 65 kilonewtons and 48 kilonewtons. 65 and 48, 1.2 and 1.5 factors multiply give us P3 value. And W is a uniformly distributed load. It has a 0.8 dead load and 0 live load. So 0.8 dead load and 0 live load give us 1 kilonewton per meters. Now for serviceability we're going to come back at the end, but first we talk about the strength. So once you calculate all these combined loadings, we can put this one on these diagrams where we have A, B, C, D, and this one is 2 meters, 2 meters, 2 meters, and 1 meters. That is given here in the questions. Shear force diagram is drawn here. From the shear force diagram, maximum shear stress is 278 kilonewtons, and the bending moment diagrams at the loading positions. For example, for these loading positions are calculated at the midspan is the maximum, which is 532 kilonewton meters. Now we need to find the trial beam which can reduce this bending moment and the shear force. So we're going to take select the grade 300. As a first case, assume the beam is fully braced and thus the member capacity equal to the shear capacity. Now in this case 5 ms is greater than maximum, so that is that maximum 530 kilonewtons, and this ms is FYZ coming from AS 4100 on page number 50. ms is equal to FYZ. Now we have taken the grade 300, so Z equal to 530 times 10 to the power 6. We convert into Newton millimeters because we have kilonewton meters, so times by 10 times by 1000 times by 1000 gives 10 to the power 6 Newton millimeters. 0.9 is the safety factor, so dividing Fy is 300, so Z value is 1976 times 10 to the power 6 millimeter cube. So that is the effective section modulus. Now we need to find the trial beam which has a section modulus greater than 1970. 530 UP 82 which has a section modulus Sx which is 2070 10 to the power 3. So that is the value we're going to take here, 2070, which is greater than 1970. So we're going to try 530 UP 82. Now first we're going to check the bending. Always we make sure that beams generally fail in the bending. The capacity, the failure mode is bending, not the shear, so we always do the bending check first before the shear. So make sure that the beam does not fail in bending, so therefore we always check the bending first. Now this is the condition. Always we're going to check whether it's a fully restrained or not. Left hand side is L over Ry. For the segments we have 2000 millimeters given in the questions, that is 2000 millimeters over ry 43.8, that is for 530 ub82, 532 ub82, ry value is 43.8 millimeters, so that's ratio give us 46. Right hand side is 80 plus 50 beta m 250 over fy. Now this equation is coming from 4100 on page number 53. On page number 53 there is a equation for I sections L over ry 80 50 beta m 250 over fy. Beta m is the moment ratio, which is the smallest over maximum moment, so that is given over the page. Beta m value is on 54, page number 54. Beta m is given that smaller to the maximum and the negative when single curvature. So 418 over 530. So if you check these segments 418 and 530, so minimum is 418, 530 single curvature, so therefore it's negative, and the beta m ratio is minus 0.48. So right hand sides we can substitute all the values, give us 38, 37. So we compare left hand side and right hand side value. Left hand side is 46. 46 is greater than RSI, then not fully restrained, so we need to calculate the member capacity alpha m, alpha s, ms. Now this equation is coming from AS 4100 on page number 30. On page number 58 we have a member capacity in close 5.6.1. we found these equations. So between C and D, so the beta m value is minus 418 on 530 minus 0.79. we just calculated that beta m value. Now moment modification factors alpha m. Alpha m is given on page number 62 on table 5.6.1. in that moment modification factors, if you can remove this UDL load, we have just a concentric load. In this case we can take it 1.75 plus 1.05 plus 0.3 beta m square. As you can see, for these particular segments, like this one, for this, let's say segment CD, we don't have any UDL loads, so for these segments we can take these scenarios here. We're going to substitute the beta m values here that we just calculated. So alpha m equal to 1.75 plus 1.05 beta m plus 0.3 beta m square. We substitute the beta m, just we calculated, and the alpha m is 1.11. That is the moment modification factor. Thank you. In the next video we're going to solve this example further. Thank you.